All right, good morning, good afternoon, or good evening, whatever it is, wherever you are. A couple of reminders as we start the week off. It's a short week. I've got Tuesday, we've got Wednesday, Thursday, celebration 2, no class Thursday, same as last time. Homework 5 also due Thursday, so please don't let that one slip through the cracks. Just please try to make sure you submit that. The late policy, as stated in the syllabus, allows you 2 free late assignments, but that's the combination of lab assignments plus homework assignments. After that, it's getting penalized. So probably best that we just try to save those or not use them at all is the best situation. PLC 12 this week is going to be a traffic light. That's a hopefully self-assessment, self-review, a little bit of something to help you keep going study-wise, looking at what you could review that would be useful. I have not posted that as of the time I am saying these words, but I will get onto that a little bit later today. Other than that, I don't think we have anything super pressing. Celebration 2 will follow the same basic mechanics as the first one. I will post the full page of questions, problems. There'll be, I think we had 6 on the first one, so there'll be 6 on this one. Thermodynamics only. There's not going to be any optics questions. There's only just trying to keep it as best categorized to each topic as possible. And the same time that you had in the first one. I will again give spaces for people who prefer to photo the work rather than, and then submit per problem rather than do one full thing. I just let you know that if you do one full document, you can just submit one thing. You don't have to submit it for every single question just because it says it hasn't been answered or whatever whatever baloney Canvas tells you about that. So that's there. Again, remember the time interval for the celebration includes taking the photos or making the PN, submitting it. So again, my reminder is make sure your internet is good. At least it's not something that's going to cause you a worry, right? Just try to control the things you can control. If you're somewhere where you're like, oh, I'm not sure if the internet's good enough, well, you're going to have that baseline worry when you're trying to go in and perform on this thing. So try to make it so that it's something that you can put yourself in a good position for. All right. Anyway, that notwithstanding, if you have questions leading up to it, don't hesitate to fire me an email, and we'll see if we have anything that we can get worked out. Other than that, we have basically finished up the topic of thermodynamics. I don't think we have anything left that would be salient in saying here, because we only have so much time and we got to get moving on to some more stuff. So I'd really like to use this week to talk about the beginnings of the modern physics portion of the class, which ultimately we only have 4 weeks, and this is a short one. I'm one less day this week, so we got just, we're rolling up, and this is just about the end of it. Also, I will say this, if you have examined the lab that I posted on Friday, get to thinking about what would be an interesting thing for you to do. I haven't gotten any, maybe I have. I should check. I'm not sure. I'm not actually sure if I've gotten proposals through because I've not looked yet. But I'll be checking because it's Tuesday today. I was hoping we could at least I could get your proposal so that I could spend some time looking at them, thinking about them. Anything wrong, I can make some suggestions in order to make it so that it's a smooth process. And hopefully after the celebration on Thursday, you'll have Friday, Saturday, you can work on it a little bit over the weekend and then put a presentation together for the following Friday. All right. So that's the idea. Same thing about that. If you have questions, let me know, and we'll go from there. So with that being said, and the idea that we have essentially finished the thermodynamics section of the course, I guess what we will do is move on to our next topic, which is going to start us off with modern physics, and it's going to be the theory of special relativity. My hope is that we spend the next 2 days talking about that, and I'll get some homework started off for you on this one. Think I'll probably get into it through the middle of next week, and then we'll probably finish that up if I'm feeling like that's about the right amount of time, and we'll spend the rest of the time talking about the development of quantum mechanics. So after that, little quick final celebration. Summer break is upon us, and it's that fast. Good. So let's start talking about special relativity. This is what we've got as our beginnings into modern physics, a little bit of history. To this subject, this relativity, the beginnings of relativity, was put forth by Einstein in a very intense couple of weeks periods, and I think about March of 1905, he thought through the ideas that he had been ruminating on for some time, and finally put forth the paper. It was published, and it was one of 3 essentially groundbreaking papers in physics that he published in this year. That's why 1905 is known as the Annus Mirabilis, which is the miracle year. Einstein had not only special relativity, he also published the theory of the photoelectric effect, which is something we will talk about when we start discussing quantum mechanics next week. And that's not enough. The idea of Brownian motion, which is the randomized motion of solid particulate matter inside a suspended fluid, or suspended inside a fluid like a liquid or a gas. Essentially, the idea of this is that these solid particles are moving around randomly due to atomic collisions, or if you like molecular, depending on what you have. But they're moving around randomly like molecular because they're getting bombarded by molecular collisions on all sides. And it's very similar to the idea of if you ever go to the big sporting events and they got the stadiums and someone throws the beach ball's bouncing around because people are hitting it. That is, so if you consider that happening at all times, that would be kind of like Brownian motion, people randomly punching the beach ball to simulate atomic collisions with a large for atoms, particle. So 1905, these 3 things come along: special relativity, which we know is groundbreaking, the photoelectric effect, which essentially kicks off the idea that light comes in small bits of energies called photons, and Brownian motion, which establishes pretty firmly the idea that atoms exist. I mean, in terms of a set of papers, I don't know if you're going to do too much better than those 3 right there. I know mine are not that good. So, but that's why he's Einstein. There you go. Einstein was 26 when he did this, and was working as a patent officer in the Swiss Patent Office. Was not able to secure himself an academic position until later, and that's a whole nother story by itself. But nonetheless, oh, and he had also just had his first child at that point in time. So a lot of things going on for the young man at this point in time. Let's talk about relativity here. So first of all, you might ask the question, what is so special about special relativity? Well, because it's describing a particular kind of motion. or perhaps I should say it's restricted to describing a particular kind of motion. And that kind of motion is motion at constant speed in a straight line where the speed is high and close to that of light speed. And this is the restriction that we will have upon ourselves. And you perhaps remember from 4A, we spent almost no time talking about constant speed in a straight line, which is also known as, I will abbreviate here for you, this is constant velocity motion. And ultimately, we are even going to go down to one dimension. We're only going to do 1D constant velocity motion. But the speed is close to light speed. And the idea of the general relativity is that we have any motion, right? Accelerated motion. This is something whereby you might consider this to be supplanting maybe like a Galilean type of thing where like pre-Newtonian even, right? Where you're just considering literally constant speed motion in a straight line. How far would you go? Distance equals rate times time. Basically the same idea. I don't know if that is a thing anymore. That was a big thing when I was growing up, distance equals rate times time. It's like, it's one of those things that gets imprinted upon you early and then it never goes away. So there you go. The idea of special is, and for us, we're only going to be considering one dimension. Should say, right, your usual x-axis perhaps. And general relativity is the thing that really supplants the description of the Newtonian way of thinking about forces and gravitational motion, right? Typically, it's thought of as a theory of gravitation. I mean, it is, but really it's accelerated motion, of which gravitational motion is one such example. All right. And by contrast, the mathematical complexity of general relativity is such that I told you it took Einstein about 3 weeks to put the touches on special relativity. It took him more than 10 years to finish general relativity. So I'll give you an idea of how complex of a subject that can be. Alrighty, so let's talk about speeds close to light speed. What happens here is that in the late 1800s, in the 1880s and the 1890s, well, even maybe prior to that, middle 1860s, 1865 is when Maxwell's equations were really put on a mathematical footing by Maxwell, but also by Heaviside, who was working with some of the mathematical notations. And it was the idea that electromagnetic waves are, in fact, light. So this is also a funny thing for us to think about nowadays, but back in the 1860s, this was not 100% connected. Essentially, what Maxwell did was he connected electricity and magnetism to optics. All of the optical stuff we've talked about, and it's been there kind of in the background, but all the optical stuff we've talked about is because we can think of light as electromagnetic waves. And they didn't quite have that until about middle 1860s, 1870. So when that came about and they discovered what the speed of light was, the question then was, okay, that's all fine. What is it that carries the light from the sun to Earth? And it was thought that there was a medium in outer space, and they called it ether. Because the reasoning here is that if I have a wave phenomenon, such as sound or water waves or something like that, there is a medium which does the waving, right? If I think of air as carrying my sound. Well, I expel sound waves because I'm able to cause air molecules to hit into neighboring air molecules, which hit into neighboring air molecules, which hit into, right? And so they make a wave known as a longitudinal wave, which I think we may have talked about, right? Kind of like like if you had a spring or a slinky wave that goes like this. The air is carrying, right? It's deforming and carrying the wave. And water obviously carries water waves. So what is it that carries the light wave? And the extension to that was whatever it is has to be a pretty special substance. It has to be essentially near, it has to be near, it's not tangible. Nearly, what am I trying to say? It's not, I don't know. Anyways, you can't sense it by touching, right? Like you can kind of do this and you can feel air hitting your hand. So we can't sense it somehow. It has to be extremely tense because the speed of light is so fast. And typically when you think about media that carry waves, the more tense it is, like if you think of a string, if I tension the string more and more and more, the wave goes faster. So whatever the thing is carrying the light waves has to be pretty tense, but it also has to have no viscosity because Earth goes around the sun and never loses energy, because if it did, we'd spiral out and we'd be living in the middle of the sun right now, and that wouldn't be pleasant. So coming up to the late 1800s, near 1900, was this big, intense search and description and characterization of what is the ether? What is the medium that carries the light waves? Now, it's not clear historically whether or not Einstein knew about the results which preceded the special relativity paper by about 7 or 8 years. But effectively, there was an experiment done which looked at the interference of light. So what basically happened was, you shine a laser beam, well, they didn't have lasers, but you shine basically a light beam this way and have it bounce off a mirror, and you shine a light beam this way and have it bounce off a mirror, and then these two beams come back and they interfere with one another. Okay? Now, if Earth is traveling through an ether which carries the light waves, then one of these paths is going to be slightly slower than the other one. And that means there's going to be an interference pattern when they recombine here. Now all you got to do is take this apparatus and turn it 90 degrees. And as you turn it, watch what happens to the interference pattern. It should change because the speeds of these things will be changing, right? This is exactly akin to sailing a boat with a river or flying an airplane with with a tailwind or a crosswind. Right? You'll find that it takes different amounts of time when you go with the current versus sideways against the current, and then you come back. So as you rotate this thing around, you would have different interference patterns. And the man who did this was named Albert Michelson, and his collaborators, Edward Morley. They never found any evidence of the interference pattern changing. And they did, by the way, really precise measurements. So leading up to this, again, history doesn't know whether Einstein was aware of these results or not, but there was no ether detected, which was really, really confusing for basically everybody involved, right? Ether, I'll just let you right here, right? This is the medium that carries light. It's the thing that effectively allows vibration to happen such that the light wave can move, just like air allows vibration for the sound wave to move. That would have happened about 1895, 1897, somewhere around there. Then Einstein comes out with the special relativity paper in 1905 and says, okay, what if there is no difference in light speed? What if there's no way to have a relative light speed? So if you're carefully thinking what I was talking about when I was talking about the boat race, right? If I sail a boat up a river with the current and then I sail it directly back against the current, this way I go sideways to the current both directions. It takes different times to go the same distance because your speed is effectively different. So if that was the case with light, light would travel at different speeds. If we had an ether, then light would travel at different speed this way because perhaps Earth was moving one way such that, you know, the ether wind was going with the light and here it was going against the light, right? Like ether was pushing it this way and pushing it this way. And here, this way, it's going across it the whole way. Einstein said, what if there isn't? What if light speed is a constant, and not only a constant, but is the same for everybody, no matter what your motion? So in this case, we start off with a very strange idea, which is not only that there is a speed past which we cannot seem to go. There is a ceiling to the speed, right? These types of ceilings and floors are very interesting to physicists, like the absolute zero temperature, the idea that you can't go below 0 Kelvin, the idea that you can't get the entropy of a system to decrease, right? I mean, with not a specific piece of it, but you couldn't have an entropy decrease overall. You can't exceed the speed of light in a meaningful way. So not only that, which by the way, by itself causes huge problems already, and I'll go over those in a sec. But not even that, the idea that light travels at the speed of light, no matter what you're doing. In other words, what he proposed is this situation here. Suppose that I have a light bulb, okay, or a laser beam, whatever you want, right? I've got a light bulb here, okay, and I'm going to pulse it on and off, okay? So it's going to create a light beam. We'll just say it's going left to right here. And I'm going to observe this light beam from a couple of different ways. First off, I'm going to just stand here. And I'm going to say, wow, look at that thing go. And this person is going to see, let's see. This person is going to see the speed of light. All right, so light, and I will say C is the universal symbol for light speed. And it has obviously it has a different value for whichever different unit system you're talking about, but the easiest one for us is the meters and the seconds, and so we'll say this is 3 times 10 to the 8 meters per second, a fantastically large number. Not like Avogadro's number, I guess, but when you're talking about having to go that fast, that's kind of fast. So if I'm just standing here and I'm watching the light go by, what speed of light do I expect to measure? I'd expect to measure speed of light being light speed. What do I observe? I observe speed of light. If I actually think about what I expect and then I go measure it, here's what I expect to happen, and that's what I observe. Now let's suppose that I'm running and I observe the light beam. So let's see, I'll try and draw a running person here. This is not going to be good because my artwork is not great, but there's somebody running. What do you expect to see in terms of if I make the measurement, in terms of the speed of light? How fast do you think light should be going now? Well, whatever your running speed is, right? You'd say, well, look, this is exactly like you're going that way with some speed v, say. This is exactly like, I don't know, riding your bicycle, driving in the car, whatever it is, right? You're driving along in the car and someone goes past you. Now, if you're still because it's a stoplight and it just changes and you're one of those like sitting there waiting for the light to change, but then this person's timed it perfectly such that they come past you, you go, wow, look at them go. They're going whatever speed they're going, 30 miles an hour. Well, that would be pretty fast through a stop sign, but nonetheless, it happens. As you start to go, okay, another person comes past you, and you'd say, well, they didn't seem to be going 30 miles an hour. They were only going like 20, right? And you look at your speed and you're going, I'm doing 10 miles an hour, and I think they're going about 20 miles an hour. Oh, so their speed's 30 miles an hour, right? But I'm observing them from my reference frame of moving. I'm observing them doing 20 miles an hour rather than 30. So would you agree that you'd expect the light speed here to be c minus v? If you're running, that's not a very fast speed compared to light speed. So what if you were in a car, or what if you were in a rocket ship or something like that? So let's put you in a rocket ship here. Let's give you a chance. Here's a rocket ship, looks kind of like a fish. Here you are in your rocket ship, and you've got rocket engines. Boom, there they go. Right, so here it is. You're traveling at some speed that's very, very fast. Maybe your speed is half light speed, which, by the way, no human has ever gone that fast. But let's suppose that it is. Let's suppose that your v in this thing is equal to 0.5 c. When you look at the light beam, do you say, look at that light beam, it's traveling at 0.5 c? And then you look at your speedometer and going, oh, I'm traveling at 0.5 c. 0.5 c and 0.5 c is c. No, that's not what happens. You expect that you should be able to, at some point, then catch up to the light beam. Well, not catch up to it, but perhaps you could go 99% light speed. And then you'd say, oh, look at the light beam. It's going only 1% of what it should be going. Okay? No, that's not what happens. What you expect to see is that the light speed changes. It does not. What we observe is that light speed is the speed of light, no matter how fast you're going. And this right away is a hurdle to get over, because it contradicts everything that we experience. We experience relative speeds all the time. And in fact, the name relativity was not what Einstein wanted to call this, because it seems like the speed of light is relative. It's not. The speed of light is an invariant. It's a much bigger deal than perhaps you're aware of. You'll find out how big of a deal it is soon. Einstein, in fact, wanted to have this known as invariance theory. He did not like the name relativity because it sounds like exactly what I just said. We experience relative velocities all the day, right? We walk around, other people walk around, you look at things and you assess their motion from your standpoint. Whether or not you're moving is not really the question. It's what does it look like from your eyes, okay? Well, it doesn't matter whose eyes you use. The speed of light is always light speed. And that doesn't matter if you're traveling 99% light speed as it is already. Because you're going to see, if you're in a rocket ship going 0.5 c, you're going to look at a light beam and go, it went past me at light speed. And that light speed is exactly the same as what you would expect if you were standing still. So the idea of something that has the same speed with respect to everybody is an odd one. It doesn't go with our natural experiences. Okay, so this is the first thing that lets you know that we're kind of sailing into some kind of strange waters here. All right. What happens is that no matter your speed, these are always c. Okay. All right, so there's the first kind of strange thing that kind of makes you go, huh? Interesting. All right, well, and ultimately, even if you were traveling at sea, which we cannot do, of course, but even if we were, we'd still see light traveling at light speed. Yeah, it's just kind of a strange thing when you really stop to think about it. I mentioned that even having speed close to light speed, even having a ceiling on the speed by itself is a strange thing. So let's discuss a couple of consequences of there being a light speed as the ceiling idea. There's a top speed to how fast we can move. Isn't that kind of strange? There's a speed past which nothing of consequence can go. You can't go past this speed. It's just kind of strange, right? It's just kind of strange. It's like, I mean, maybe you can kind of get over the idea that I can't cool something past a certain temperature. Maybe that's like, all right. But the fact that it feels like if I run, suppose I run really well, but if I push myself, how can there be something which tells me, you can't go past this speed. You can't run faster than this. Right? Like I'm in a rocket ship. I get my engines going. I should be able to provide thrust by which I can accelerate and get faster this way. And eventually there's going to be something going, no, you got to slow down here. You're getting close to the speed limit. It's like, really? Can't I just turn the engines on higher and go? No, you can't. So the idea to this, this is going to now hit Newton's second law. Newton's second law tells us that the sum of external forces results in a time rate of change of the momentum. Okay? In other words, I can change the momentum. I can change my momentum if I'm getting pushed by something, right? And that's exactly the same thing with the rocket ship here. I'm going to flip the engines on. I'm going to get pushed by the expulsion of my rocket exhaust, and I'm going to accelerate. I'm going to pick up speed. I'm going to change my momentum. Off I go. So if there's a ceiling to speed, this can't be right all the time, can it? If there's a top speed, then this has to not be true at some point. Because if I get near that top speed, if I get close to that top speed and I exert or something exerts an external force on me, and now I'm achieving light speed, and something exerts a force on me, I can't go faster. So I can't change my momentum anymore. How do I change my momentum if I can't move faster than I'm going already? All right, so that kind of tells you that this has to be modified. We have to figure this out at some point, because If I think of a graph of velocity, and here's what we know now. I'll put in a little bit of this now. There's a factor by which we assess how fast we're going, right? So there's a speed ceiling, and there it is. Can't go faster than that, which means that if I accelerate and accelerate and accelerate and accelerate, I can increase my speed given a particular external force, right? But ultimately, I actually went across there. Right? This is what has to be happening, right? This is the essentially P, right? The momentum increases as we expect to a certain point, and then it starts to, well, you can't go faster than V. So what are we doing? I mean, you can't go faster than C. Your V cannot exceed C. So we got a few things to talk about. Hopefully that whets your appetite a little bit. We're going to start by looking at some space-time diagrams. In other words, the major picture by which we are going to assess the outcome of a switch in perspective is going to be by the space-time diagram. Because ultimately, let's talk about the question special relativity wants to answer. And it's the exact same question that has been around for thousands and thousands of years, which is, what does that look like from that perspective? If I move over there, or if I move this way, or if I'm moving some way, what does that look like? Right? That's all it's saying. So you go back to the idea of you sitting in the car at the stoplight. The light turns green. You're about to start moving, but have not yet done so, as somebody zips past you in the outside lane here, going fast. Okay, you see them, right? You might then ask your question, what do I look like to them? And so you could put yourself in their seat, and what would you see? You'd see yourself going like this. Right? You'd see, oh, look, there's a car and a stoplight, and they're approaching me, and now they're going behind me. It's as if they are moving, right? From the perspective of the person who is going 30 miles an hour as the light turns green and keeps going, what it looks like is that the car you're sitting in goes past you this way. Special relativity just attempts to answer that for cases in which the speed is close enough, or it's a significant enough fraction of light speed. Because it turns out that the answer gets not straightforward. Okay, so I want to talk about the space-time diagram here. Let's do this. I'm going to attempt to draw a set of objects whose motion we wish to track. Let's suppose here that there's a tree here. No, it's a bigger tree than that. Let's make it a nice big tree. It's a redwood. We live in the Santa Cruz County area here. We live near the Central Coast, or most of us do. So we have redwoods over here. I'm not sure what you have where you are, but we have tall trees, and that's what they look like. Moving past the tree, we have a car. Let's say car moving. Right, car's moving that way. Some speed v, and let's say that we also have somebody standing under the tree throwing a ball. Not going to draw the person and all the stuff going along here, but suppose we also have a ball. There's a baseball going, and it's going at 1/2 of v. Whatever the speed of the car is, baseball is going half that speed. So here they all are at time equal to 0. Okay, now I want to examine a couple of snapshots, and I want to overlay the snapshot drawings on top of this drawing. And that's how we achieve the space-time diagram. All right, this is for time equal to 0. Whoops, let me do this. Let me do this, time equal to 0 here. And you can see that they all basically have the same position. I tried to draw the tree here. It's through the middle of the car and through the middle, approximately-ish enough, of the baseball. The next time interval, say time going to 1 second, what am I going to draw here? Well, I'm probably going to say, okay, in 1 second, the car, let's say the middle of the car has gone 2 spaces. Well, no, I'm going to have to make it go more than 2 spaces. Maybe it's gone 4 spaces, right? So here at t equal to 1, the car is now here. So I'm going to draw the car here. Whoops. Right, there it is. Well, it looks like it's going that way, so it should go like this. There you go. Car moving this way, some speed v. And now we're at time equal to 1. At time equal to 1, if the car's moved 2 spaces, then the ball has only moved, if the car has moved 4 spaces, the ball has only moved 2 spaces, which means it's here. Like so, 1/2 v. Right? So here at t equal to 1, the car has moved some distance, the ball has moved half that distance. If I draw the next time, the car is going to be here, the ball is going to be here, right? Notice that this is what it looks like from the tree perspective. In fact, I'm going to go ahead and do that. So if I go 1, 2, 3, 4, so the car is here now. Oops. Got the tire a little too close to the rear bumper here. All right, so the car is here now. That's at t equal to 2. Ball is now here at t equal to 2. All right, this is t equal to 2. Okay. So from the tree perspective, the tree has not moved. I'm observing the position and relative motion of the car from the tree frame. I'm observing the relative motion of the baseball from the tree frame. Okay. Now the question comes in, okay, what does this all look like from the baseball perspective? Maybe you can kind of see that without having to do a whole bunch of calculations. If I jump onto the baseball, how fast am I going? I don't want to say that's a trick question because I don't ask trick questions. It's a question that you need to think about carefully. When I jump onto the baseball, well, first of all, we were in the tree frame and you would say, well, I was stationary. We weren't moving. Okay. If I'm in the baseball frame, now it looks like the tree's moving, doesn't it? Go back to that car example. Sitting here, car goes past. If you're in the car going past, other car moves this way. So when I say, if I jump onto the baseball, what speed am I doing? The answer is 0. I'm not moving. And how do I know that? Because the easy way to find where the origin is, you all have coordinates, right? We all have to have a set of coordinates to measure where things are and how far away I need to go to do this, that, or the other. The origin of the coordinates is always at your feet. So if you look down and you see your feet, then that's where the position equals 0. Anytime you look down at your and see your feet, your position is 0. And therefore, your position never changes over time, because I'm pretty sure you can always look down and see your feet. Therefore, if I jump onto the baseball and I look down and I see my feet, I'm not moving. What I do see is the tree moving past me at 1/2 v this way, right? I see the car moving away from me, not at v anymore. I see it moving at 1/2 v away from me this way. So one thing to keep in mind as a mentality is that, and by the way, I also encourage you to speak this way, just as we did in the last section, where I want you really to come to terms with the difference between temperature and heat. Being careful about saying, I'm heating something up. Really? I'm only doing work on it. How did I heat it? I didn't. I worked on it. But its temperature went up. Okay? So thinking about really speaking about things in a more precise way, we're going to try and do the same thing here. Okay? Whenever you think about how fast am I going, you're never moving according to yourself. You're always stationary. Everything else moves around you. Okay? So anyway, a mentality to think about, right? That whenever you change frames, how fast am I going now? Well, you're going zero because you're always going zero. You look down at your feet and that's where zero is. If zero's there and your feet are there, well, then you're moving at zero because your position hasn't changed. All right. So what we have here is the ability to think about the position of the car as time goes on and the position of the baseball as time goes on. Now maybe instead of drawing it kind of like this, maybe I can draw it a little bit differently. Maybe I can draw it in a perspective sense. In other words, if I take these future time shots of the positions of the ball and the car, maybe I can draw them such that I can show you how we think about space-time diagrams. So let me do this. I'm going to take these and I'm going to kind of stack them behind the time equals 0 one. I'll show you what here. I'm just going to take these away here. Take these away here. Okay. So now if I want to think of time equaling 1, I'm here and and now I want to go to time equals 1. What I want to do, let's see if I can do this. It takes planning. It's really easy when you do it, but when you have to actually draw, when you see it, it's easy looking, but when you have to plan it, it's not so easy. All right, so I'm going to stack behind this one. I'm going to stack the time equals 1 perspective, which was car traveled 1, 2, 3, 4. So it's going to be here. All right, so I'm going to put the car now here. Whoops, not a very good car. All right, so there's my car. The ball is now, and I went up 1, 2, 3, 4. And I go up 1, 2, 3, 4. So the ball is now here. Right? That's moving at speed v. That's moving at speed 1/2 v. And the tree is still here. Okay, so what I'm doing is I'm taking these 3 objects and I'm drawing their next position according to the run-on of the clock. Right? So at time t equals 1, the tree is still here. The car is now over there. Right? From the perspective of the tree, the car is there, the ball's here. I think I got that right. I didn't, so I got it back. Oh, it should have been over here. That's too close. It should be here. All right, but you get the idea, hopefully. If I want to draw it again, I can put another car back here. 1, 2, 3, 4. It's about here. Right, so here's the car at time equals 3 seconds. It's almost like you're taking, you can't see it from this perspective, right? But it's almost as if I'm taking time equals 0 and then time equals 1 and then time equals 2 and then time equals 3. I'm putting them behind like this and then kind of turning it so you can see it like this. So you could actually draw the position of the car as something like that. And you could actually draw the position of the baseball. I need to go over 2 and up, so it's here. The position of the baseball like that. And the position of the tree like that. Like so. All right, and this is how we construct our space-time diagrams. It's this idea of plotting the position this way as time goes on. Oh, I gotta plug in my computer real quick. Sorry, hold on a sec. I'm about to run out of battery. Okay. Go here and we'll go here. All right. Good. Okay. That's the space-time diagram. Now, what I want to encourage is that what if I jumped onto the baseball frame of reference, which is this line here, okay? This line up here. If I jump onto that, what do I see? Well, I should see the tree kind of going this way, right? The tree's position, as you can see, is going away from me. In other words, here's the baseball frame of reference, and this distance here is getting larger. Well, the tree is leaving me, right? Just like the car is leaving me this way. I'm seeing the cars going that way, right? So I from my perspective here, I see the tree going to the left and the car moving ahead of me, if you like, further to the right. If I'm on the car frame, right, if I jump into the car and I look at what's happening, well, now I'm going to see the baseball is getting further away from me, but the tree's really getting further, like the tree's going way faster and going that way, right? This is the question special relativity tries to address, is what do things look like from different points of view? That's all we're trying to get at here. The only difference to this question, which by the way was answered by Galileo in like the 1500s, is what happens when things get really fast. Because we've introduced this one extra piece, that there's a ceiling to the speed, and that everyone sees light speed being the speed of light. No matter if I'm stationary in the tree frame, or if I'm moving with the ball, or if I'm moving with the car, it doesn't matter. We all measure, we all get together and say, hey, how fast was that light beam going? And we all say the exact same number, okay? Whereas if you're in the tree frame and you ask how fast the baseball is moving, you'd say, well, it's moving at 1/2 v. If you're in the baseball frame, you go, how fast is the baseball moving? You go 0, because I'm sitting right next to it all the time. The tree, though, tree's moving that way at 1/2 v. So anyways. This is what we're going to do. We're going to construct space-time diagrams, and what they're going to do is this kind of a special thing. On the space-time diagrams, there are going to be the perspectives of different moving objects, moving relative to, say, Earth frame like this, right? Such that when you consider how do I look and see what's happening from that perspective, you should be able to look at that. Because you've got two axes on the same, axes on the same plot, right? So we can see the motion of two objects at once, just like we can see the motion of three objects at once on this plot right here. Okay, so let's start and see what we can do here. I want to introduce you to how we're going to make these space-time diagrams. In other words, what is going to be the outline of the axes. It's going to be backwards from your 4A way of thinking. Actually, it turns out the 4A way is backwards from what we should be doing. But that's for convenience, because when you do the 4A graphs, the slope was the velocity. Well, that's not true anymore. We're going to do x here and t here, like that. And this is called the space-time diagram, hopefully for obvious reasons. And what we're going to do is, for convenience, we have to abandon the meter as our distance measurement. We have to, right? Otherwise, our times and distances are going to be ridiculously large when you consider the measurement of c in the SI system, right? 300 million meters per second, and I got to deal with that. If I think about graphing 300 million meters per second on a set of axes like this, what is my line going to look like? In other words, how far do I have to go before it goes up at all? If I'm graphing in the meter and the seconds units, right? This thing, I have to go 300 million meters this way before I can go up 1 second. This is not useful. What we have to do is make C visible on a graph like this. So what we're going to do is make C the 45-degree line. That's going to be our speed of light right there. Okay. So essentially, we're setting C equal to 1, right? That's the line of slope 1, right? You go over 1, up 1, over 1, up 1, over 1, up 1. That's a 45-degree line. All right. So if that's our line of light speed, well, then all of the other speeds that we deal with have to be up in here because they're slower than light. In other words, it takes them longer time to go the same distance, or it takes them, or they go the same amount of time, but less distance, right? So remember, it's backwards from your regular graphs. So all of the speeds lower than light are in here, not over here. They're up here, okay? First thing we need to do then is set C equal to 1. And this is going to be the benchmark by which we assess how fast something's going. So if you like, you can form a ratio. You can form the ratio of V divided by C. And that's going to be a fraction now, right? Instead of talking about how fast are we going, we're saying how fast are we going relative to light? Okay, so if I'm going, for example, 0.3 or 0.8 or 0.999, you know how fast we're going because this is a ratio of your speed compared to light speed. I'm going 30% light speed or 80% light speed or 99.9% light speed, right? So we're considering the ratio of V over C. That's exactly akin to setting C equal to 1. Slash or, I guess, if you like. Okay. Now, if that's the case, and we're going to deal with a set of space-time axes like this, then we have to modify the axes for when something is traveling. Just like I did here, for example, the faster thing, the car, has a more, or say less steep slope. It's more shallow. I don't know. It's more towards the horizontal than the ball speed, right? So slower speeds are more up, faster speeds are more this way. If I think about plotting the baseball's motion on this graph here, then I might say, okay, well, it looks like this, like that, okay? And I might say that I'm going to call that like the T prime axis or the T of the baseball. I'll call it T, yeah, I'll just call it T prime. T prime. That's the baseball axis. This is what Galileo would tell us to do, right? Because when Galileo comes in and says, well, if you want to know the position of something from a moving reference frame, all you have to do is subtract off the position. So in other words, if I'm here in the baseball frame and I want to find out what is the distance from me to the car, well, I should be able to find that out because effectively the car for me is moving at 1/2 V. And all I have to do is say, oh, okay, I'm here now. And how far away is the car? Well, it's this distance plus that distance. In other words, it's the distance I traveled away from the tree plus how much further the car went. No problem, right? And that's exactly what we're seeing here with the T prime axis. The problem comes in, however, when we consider light going in, say, the negative direction, which puts it right here, right? That's also a C line, but that's the C of a light beam going that way instead of a light beam going this way. Assuming that to the right is positive, which I guess is fair. Now we run into a problem. And here's the problem. The problem is, if I'm on the baseball and I'm traveling, I'm on the T prime axis now, and as I am on the baseball, here's the baseball, and it's moving at 1/2 V with respect to Earth, and I pass a light bulb here, and a light bulb, well, I don't even care if there's a light bulb there, doesn't matter. I got a light beam going this way, and a light beam going this way out of the light bulb. If I'm moving this way, then what speed do I measure this light beam to be traveling at? Well, everybody measures light speed to be the speed of light. So I should measure that light beam to be moving at speed c. But should I not also measure this light beam to be going at speed c as well? I certainly should. Therefore, for me on the baseball, the distance, as time goes on, the distance to that light beam should equal the distance to that light beam. Told you it was a little strange, but look how our graph does not show that. If I'm here on the baseball and time has gone forward, the distance to the front light beam does not equal the distance to the rear light beam. So we have to fix this. We cannot use the space-time diagram as I have drawn it here unless we make a modification. Okay? Do you see my issue here? If I'm on the baseball and I'm traveling along the T prime axis here, I, according to this graph, see the speed of, I see the distance to the light beam ahead of me as being shorter because presumably I'm moving with it, versus the light beam distance, the distance to the light beam that way, which is kind of like I'm moving away from it and the distance is separating. Whereas this distance is also separating, but not quite so much because we're moving the same way. Right? So this distance here is less than this distance here, but that shouldn't be, because we just got done telling each other, or I assume you would tell me the same thing. So that light beam is moving at c, that light beam is moving at c, according to someone on the baseball, because light moves at the speed of light. That's not being reflected here, so we have to change our axes slightly in order to make this this adjustment. And here's what we have to do. We have to change how we measure things at the same time kind of idea, all right? Here's what we're going to do. Instead of measuring across like this, which is apparently at the same time relative to someone in the t-axis here, what we're going to do is we're going to tilt it so that, let's see here, I'm going to measure, I want to measure a distance about like that. That's going to be too much. Maybe like this. Oh, that's pretty good. That feels like it's almost, yeah, it's close. It's about like that. Right? In other words, these distances are pretty close to each other, which means that I have to change my space axis to now be this. And I'm going to call that the x prime axis. All right. So our moving object has a completely skewed set of axes. Typically, our 90-degree orthogonal usual ones are Earth frame, right? That would be these ones right here. Notice what I have to do.
If I take the t-axis and I incline it this way to become the t prime axis, then I have to take the x-axis and incline it this way to become the x prime axis. Essentially, I'm squeezing them both in symmetrically about the C line here, the 45-degree line. And just to make this abundantly clear, this angle here, call that theta. That's the same as this angle here, call it theta. They have squeezed in, right? Instead of doing this, we're going like this, such that the 45-degree line is still directly in the middle of the two axes. That's what a space-time diagram looks like. And by the way, that's a special relativistically correct space-time diagram, which is even better. Okay, so when we plot things on a space-time diagram, we are going to have to expect to see lots of stuff going on, and we need to be able to interpret these things. All right, so let me show you this. I'm going to try and give you a quick example because we're just about done. This will be perfect. You can think about this one tonight. We'll come back tomorrow and see if we can't get a good answer on it. Okay, but of course that means you actually have to try it, and don't be lazy and forego this. All right. So we're going to do this. I'm going to take a person standing here like this. Okay, like this. I'm going to say there's a person standing here. Okay, that person's right here, and I have a couple of lamps. Say I'm standing on a street, and there are light posts. Okay, these light posts, and they're spaced evenly. So I'm going to put two and have a lamp here. And I'm going to go two and have a lamp. I'm going to go two and have a lamp. I'm going to go two and have a lamp. And I'm going to go two and have a lamp. Okay, now, yes, they look all like lollipops or balloons or whatever, but they're lamps, and you can see that they're lamps. So what I'm going to do here is I'm going to turn these lamps on in a specific order. And the question then is, okay, if I'm in a car driving past, what ordering do I see? All right, so we're going to make this the x and the t-axis here. And I'm going to say that lamp, we'll call this lamp A, B, C, D, and E. These are going to turn on at specific points. All right, so let's suppose that lamp A, let's say I'm going to call that, I guess I'll call that point 1. I don't know. Sure, why not? We'll call that point 1. Call this point 2, point 3, point 4, and point 5. Okay, these dots represent the points in time when the lamp turns on, according to this person here who is stationary and sitting on Earth. In your notes, I want you to write down which lamp turns on first, and then second, third, fourth, fifth. Okay? In other words, if I'm this person, which lamp do I see turning on first? And when I say see, I mean like I have to be careful with this because I don't literally mean visually seeing. What I mean is if I did a bunch of calculations, I could tell which one turned on first. All right, and that's kind of a funny thing. It's a funny caveat to say, and I'm sorry about that without putting it into context, but let me do that in the next class. We'll talk about the difference between seeing and observing. Suppose that I'm an omnipotent being, right? And I am able to see this graph, even though I'm just a person here. Okay, which lamp turns on first, according to this graph and that person? Okay. That's the first thing. Now I want to say, here you are, or here's your friend, and they're in a car moving that way at some speed v. I have to now draw their axes. Here are their axes. This is going to be a t prime axis going like this. Whoops, that's not very straight. Sorry about that. I'll bring in a long straight edge next time. And that means I need a 1, 2, 1, 2. Whoa, come on. 1, 2, 1, 2, 1, 2. I don't know if I'm quite getting this right. There's the x prime axis right there. All right. Now, from the person in the car, what's the order that the lights turn on? That's the question. Okay, and that's it. According to a person on Earth, what's the order that the lights turn on? According to someone in the car, what's the order that the lights turn on? The answer is different for these two people. Okay. The next question we're going to ask after that, and we'll explore this as I see I'm just about out of time today. The next question we're going to explore after that is, okay, what happens when we see the light from the lamps? In what order do we see the light from the lamps? And that's a different question, if you can believe that, which you should, because we're going to answer it next time. All right. The question is, last time, from the person who is at rest on Earth, in what order do the lamps turn on? From the person who is moving in the car with respect to the person here on Earth, what order do the lamps turn on? And if you can answer those, then you'll be a step towards understanding some special relativity a little bit more. So I'll leave you to think about the answers to those questions, and we will come back in the next video and answer them. I'm going to say tomorrow, but for most of you, it'll just be in the next video. All right, happy rest of your beginning of Special Relativity Day, and I will see you next time.